Hello, guys.
Hello.
See you.
Hello.
Hi.
Hello.
Doing?
Good, thank you.
Okay. Also, well. So talking about our previous this postponed lecture, which was on Sunday. Yeah. Good afternoon. Hello, everyone. So not many people attended, but I mean, probably was not so easy to arrange. Yeah, that's not a problem if you forgot to attend the previous lecture. Yeah, it was recorded and also available online. So it's on the same with the same link as I send you with the welcome email, so you can find it recorded. So the key message from the last discussion, which was on Sunday, we considered damped oscillations, and what is mandatory to know, you need to know the final equation specifically for under-damped oscillations when we have not very strong damping, like not very strong drag force, which allows with some disturbance initial system like spring block system to still oscillate, but with exponentially decaying amplitude over time. So that is the there is a equation given in the textbook which describes at which frequency it will oscillate. So it will be not the intrinsic frequency of the block string system. Yeah, hello, nice to see you guys. But it will be affected by this drag force. And also before the trigonometric function, which gives us this periodicity, it will be amplitude times some decaying exponential function. So it will tell us that this function, this amplitude will decay exponentially over time. So these are key things which you have to know and be able to explain. However, in this lecture, I try to derive step by step this equation. It's a bit bulky, not so straightforward, but for those who are interested where it comes from, so you are welcome to go through that lecture. But again, what is mandatory is just to know the final equation and be able to understand each terms of this equation, what it stands for. Yes, you are right. Today we start a kind of new topic, but this topic is related to the previous one. So it was oscillations. The previous one, this topic which we discuss today and during this week will be waves. And it's kind of a smooth transition from previous topic to this one, since if we were talking about some oscillator previously, but obviously if this oscillator is in some environment, it will create some disturbances, like periodic disturbances in this environment, and they will form waves which can spread in this environment. So depends on, let me maybe switch camera and share my screen. 1 second. Interesting. 1 second. Share. Yeah, okay. So let's say we have environment like medium is some string attached to the wall. So if we shake it once, so we don't have periodic disturbance, just once we shake it, we have some movement of elements of the string up and down. Within this pulse, which and the pulse itself moves along the string, let's say along some axis x. So what is the key feature of such a pulse? Or if we have some periodic disturbance, then we form a wave which moves along the string. The main feature is that we don't move elements of the string in x direction, so they move only in y direction. But energy of the wave is moving in the x direction. So we can transfer energy, but in certain direction, but we don't transfer matter in this direction. So this is a main feature of the wave, and depends on the orientation of displacement of elements of the medium with respect to the direction of the spreading of the pulse or wave. We can define two major types of waves. So first one, which is classical example, wave along a string, we have a so-called transverse wave when elements of the string move up and down while the pulse, like this wave, is moving from left to right. So they are moving in perpendicular directions. So that is so-called transverse wave. And there is another example here with this coil string. When we disturb it, sorry, when we disturb it back and forth, we create some periodic regions of the string with constrained region and stretched region. So these periodic constrained and stretched regions will move as a disturbance along this string. And in this case, elements of the string will move in the same direction. Displacements of the elements of the string will be in the same direction as not the same direction, but the parallel, not perpendicular, but parallel to the direction of the spreading of this wave. So this type of waves is called longitudinal wave, and all waves which are possible in nature, they can be classified as either pure transverse longitudinal or kind of a mixture of two. And one of interesting example is wave on water surface. So in this case, particles of water on the surface, they perform kind of circular motion. And there are two components, part responsible for transverse displacement that comes from the variations in the vertical position of water elements, and also longitudinal from moving back and forth. So if we want to quantify the wave, we need to deal with so-called wave function. So let me stop sharing for a second. And wave function, it's function which gives the relationship between displacement of the elements of the environment where a wave is spreading. Let's say it's a string. So displacement of elements of the string in y direction as a function of position and time. So this is a wave function. And we also may assume that the shape of the pulse or shape of the wave doesn't change in time. So we can write that, for instance, y at any x at 0 time, like t equals 0, will be given by some function f x, and that will give us the shape of the pulse or shape of the wave, which will not change. The position of the pulse will change because it will move from one position to another over some time interval. And taking into account that the shape doesn't move, doesn't change, we can, let me share this screen again. We can look at this pulse here. So we have initial position, like this maximum is at 0 x, and it moves with certain speed along axis x to the right. So in time interval v times t, so in time interval t, so the distance this wave pulse will travel along axis x will be velocity times time interval t. And we see that the shape is the same, so shape didn't change. However, if we pick up some point P, which represents some small element of this string, its position y, displacement along axis y, will be given as position of element of this string at a distance if v times t. So we wait until this pulse will move to the point P with coordinate, its coordinate x, and that will happen in time interval v times t. So we can kind of predict what will be position displacement along axis y of this point P in time interval v times in time interval t. So in order to specify it in like quantitatively, we can write that y x and after some interval time t will be equal to y x minus vt at time 0. So this is when our pulse is moving from the left to the right. If pulse is moving from the right to the left, we will have similar format, but instead we will have plus here. So we will, it gives us an opportunity to predict the position of some element of the string at some interval time t, when we know that shape of the pulse doesn't change, and we know also the speed this pulse is moving either to the right or to the left. So now let us consider some traveling wave, and let me share again the screen. So we have at time equals 0, so we look at this figure, some shape of this wave. We have some sinusoidal wave created by some simple harmonic oscillator attached to the string. So this is displacement y versus position x. So since it moves along the axis x at some time t, some time interval, this shape will move forward, and there will be some distance between this previous and current position of the wave. This is how it moves along axis x. So if we consider plots of the displacement y of elements of the string along axis y versus position x and versus time. So we can define two main properties of the wave. So besides amplitude, because amplitude is just maximum displacement of these elements. So it's the same on both figures. But the distance, if we have displacement versus position x, the distance between two adjacent points with the same phase will give us wavelengths is one of key parameter of the wave. So it's called wavelengths, lambda. And if we have displacement versus time, then distance between two adjacent points with the same phase, it could be like two minima, two maxima, or it could be just two arbitrary points, but they have to be in the same phase. That gives us period of the wave. Another important parameter, obviously, that wavelengths and period will be related to each other. We will discuss this later. So the relationship between them will be via the speed of wave traveling along axis x. So let me stop sharing. And now let us assume that, as I mentioned, we have some simple harmonic oscillator. We create sinusoidal wave. And let's assume that y at position as a function of x at 0. So it gives us some shape of the wave at fixed moment of time will be equal to a times sinus a small times x. So
excuse me, Professor, I have a question. What is small a? Is it acceleration or what?
Oh, yeah. So, yeah, good question. We are just planning to discuss this. So capital A is the amplitude, and this small a is some constant, because we want to derive the general form of wave function, but we start from some approximation. So we don't know yet which constant it is. It's just some constant, but it is to be determined now.
Okay, thank you. Sorry.
You're welcome. And now we want to define what constant it will, it should be. And that is based on some conditions. So first of all, we know that for sinusoidal wave at x equals 0. So if we have this sinusoidal wave, let's show it here for more clarity. X, y, here is our sinusoidal wave. So distance from here to here will be our lambda. And at x equals 0, that will correspond to y 0, 0, means x0 and t equals 0. Our displacement along axis y, a times 0, will be equal to 0. So with this, is clear where we start. Now, we need to consider at which distance x this displacement y will also be, again, will be equal to 0. So do you see it from the image?
Yes, it is half of wavelengths.
Exactly.
And one wavelength and 3 divided by 2 wavelengths.
Yes, but we care only about the closest point from 0 when y is equal to 0 again. So that is absolutely right. At distance half of the wavelength. So
Excuse me,
yes.
could you repeat please the last statement?
So we define that for this sinusoidal wave at x equals 0, displacement along axis y is 0. So now we want to define at which minimum distance from this position x equals 0, displacement will also be equal to 0. And this distance from this plot we see, if this is wavelength, a distance between two points which are in the same phase, then displacement y will be equal to 0 again next to this point x equals 0 at point x equal lambda divided by 2. So now we know that y is equal to 0 at x equals 0 and also equal to 0 at x equal lambda divided by 2. So let us take this into account and write down in the wave function. So y at x lambda divided by 2 and time 0. Now we are talking only about some shape of the wave, which is kind of frozen in time at some given moment of time, which is 0. That will be equal to amplitude times sinus small a times x, which is lambda divided by 2. And that we know will be equal to 0. From this plot, it is clear. So that means, assuming that a small, this constant we want to determine, is not equal to 0, then it's possible only when a times lambda divided by 2 is equal to pi, which is pi radians or 180 degrees. From here, we can define our constant small a, which is equal to 2 pi divided by lambda. Now, since we already know this constant a, we can write the equation for the shape of the wave at fixed moment of time. And that will be, let's write it already in the next slide. Y as a function of x at 0 time will be equal to a amplitude times sinus 2 pi divided by lambda times x. Okay, so we have this. Now next step, we want to present it also in the form as a function not only of position, but also of time. So not just frozen in some moment of time, but also define displacement y at any position and at any moment of time. So in order to do this step, and to provide information of y as a function of x and t, we need to do the following. So 2 pi divided by lambda, and here is x. We need to assume that this wave is moving with constant speed and constant shape, so it doesn't change either to the right or to the left, what we considered previously for just a pulse. So here, if it moves from, for instance, from left to right, we can write here x minus b times t, and we close the parenthesis which defines the argument of sinus. If it moves from the right to the left, then we will put plus here. So now let us go further. From the definition of the parameters of wave, we know that the wave will travel distance delta x equal to the wavelength in time interval delta t equal to the period of the wave. So it comes from definition of these properties of the wave, lambda and capital T period, the wavelength and period. So taking this into account, speed of wave can be defined as delta x divided by delta t, that is equal to lambda divided by t. So as I mentioned before, there is a relationship between wavelength and period of the wave, where the speed of this wave in given environment. And we can also write that it's equal to frequency times lambda, where frequency is 1 over period, is how many periods fit in 1 unit of time, 1 second, for instance. So now let us substitute instead of v speed, this expression, lambda divided by period. So in this case, our wave function will be given as amplitude times sinus 2 pi lambda divided by lambda times x minus lambda divided by t times t time. Okay, now let us put this lambda under 2 pi in the parentheses. So it will be a times sinus 2 pi x divided by lambda minus t time divided by period. Okay, so this is already a very nice form of the wave function, and it tells us, like shows clearly, that this is a periodic function. Means that y displacement will be the same, will have the same value at x coordinate, at x plus lambda, at x plus 2 lambda, so on. The same stands for time, t, which will be t plus 1 period, t plus 2 periods, and so on. So we can actually show this. Let's say we claim with this statement that this is periodic function. So it means that we can write x divided by lambda minus t divided by period should be equal to x plus lambda divided by lambda minus t plus period divided by period. So now we indeed can show this, because it will be x divided by lambda plus unity minus t divided by period minus unity. So these guys cancel each other, and we eventually get x divided by lambda minus time divided by t. Like period. So it actually is the same as initial. So it means that we indeed have some periodic function which describes this wave. However, we still would like to make one more transformation of this wave function in order to write it in more common and kind of convenient format. Let us do it. Let's write again this wave function on next slide. And let's see what we can do with this. So y as a function of x and time is equal to amplitude sinus 2 pi x over lambda minus t over period. Let us put, open this parenthesis by multiplying with this 2 pi. So what we will get? That will be a times sinus 2 pi divided by lambda times x minus 2 pi divided by period times t. Okay, now what we can do, we can make some substitutions. First, we can introduce a new parameter, which is angular wave number, k, that is equal to 2 pi divided by lambda. And second, we need to use angular frequency. Angular frequency is equal to 2 pi divided by period, which is actually here. So this is already equal to angular frequency. So now we can do the substitutions and write the general form. It will be x function y x of x and t. So wave function is given as amplitude times sinus k x minus omega t. So this would be not the most general case because it would assume that at x at t equals 0 we would have y equals 0. So initial phase constant should be equal to 0. But it's in general case is not true because it can start from considered from any initial constant phase. So then we need to put here plus p. And this is the general form, most common for wave function, which provides us whole necessary information about the wave and in particularly the displacement of small elements of the string along y direction as a function of position along x direction and function of time. Since we have such information, we can also get information about velocity and acceleration of elements of the string along axis y. So for that purpose, velocity of this element of the string will be equal to first derivative of wave function over time at x equals the constant. So at some fixed position, we can take this first derivative, and that is actually so-called partial derivative of the function of two variables. So we have two variables, x and t, and in order to get velocity, we need to take derivative over time. So it means that we will take partial derivative of this wave function y, assuming that other variable x is constant. So that is dy over dt. and that will be equal to minus omega times A times cosinus kx minus omega t plus phi. And the same, like next step, we need to take second partial derivative of wave function over time in order to get the expression for the acceleration of this small element. That will be d squared y over dt squared equal to minus omega squared times A times sinus kx minus omega t plus p. So we will get the maximum values of velocity and acceleration. So what it will be, v maximum will be equal omega times A. So it's just maximum value, because it could be either positive or negative velocity, but that will be defined by the position and time. However, we take just maximum like amplitude of this velocity, amplitude value. So that will be true when y displacement is equal to 0. And also maximum acceleration, a maximum equal to omega squared times A equal, so it will reach its value when y is equal plus minus amplitude. So summarizing, we considered the some disturbance in environment, which can be either single disturbance, so then there is some pulse which is created and travels along the environment, or it can be some periodic disturbance formed by some simple harmonic oscillator. Then we create some sinusoidal wave, which also travels along the in the environment. We introduced two main types of waves, which is transverse wave when we have motion of elements of the string, for instance, perpendicular to the direction of the wave propagation. And we have another type, which is longitudinal. So when the elements of the environment move parallel to the direction of wave propagation. So these are two main types of waves, and it could be either pure transverse or longitudinal, or a mixture of them. Another important thing which we considered today, we derived the wave function, which provides information on the position, on the displacement of elements of the environment as a function of position x and time. So it means at any given moment of time, we can tell, and any given position x, we can tell what will be the displacement of this element of the string along which the sinusoidal wave created by single harmonic oscillator is moving. Based on this information, we actually presented in the most convenient form, including this new parameter angular wave number wave function, and we can calculate also velocity and acceleration along axis y for any element of the string based on known wave function by taking partial first and second partial derivatives of this wave function over time. Okay, we have some question. Yeah.
Could you please repeat what is K?
Oh, K is a new parameter, which is angular wave number. It's called angular wave number. It's equal to 2 pi divided by lambda. It's kind of very common in spectroscopy because very often scientists operate with wave numbers, not with the wavelengths. So it just comes more convenient for analysis of different spectra. And of course, that's also all related to the wave nature. So it's just some parameter which is convenient to use in order to make the wave function more compact and easier to work with. Okay, if you have any additional questions, you're welcome. I think this is everything what we wanted to discuss during this lecture, and we will continue learning more about waves on other discussions during this week. So our next meeting is Wednesday. Hope to see you all there. Take care.
Excuse me.
Yes.
Could you please show us one wave, one total wave?
What do you mean one total wave? I think that
Okay, is the number of angular wave number, right?
so we can check, for instance, where is our, like this. Actually, we have sinusoidal wave, which is depicted here as a total wave because we have 2 points which are in the same phase. Means since taking into account the periodicity of the wave, this part of the wave between 2 points with the same phase will just be reproduced infinite number of times.
So it is one wave, right?
Yes, it is. It is full information about the wave because it gives us the amplitude, which is the distance along axis y to the maximum displacement, like maximum displacement along axis y. It gives us lambda, and if we know the velocity of spreading of this wave in the environment, which we will do calculations like derivation of this velocity of spreading of the wave during Wednesday, I believe, during our meeting on Wednesday, then we can also get the period of the wave. So we actually have all information about the wave.
Okay, thank you.
You are welcome.
Professor, excuse me, I have a question. I have a question about our final equation that was like A sinus kx minus omega t plus phi. So would that equation change if we, for example, consider that our wave moves from right to left? And how would that change?
Oh, so that would be at this point, when we introduce time dependence, here, you see that if we move, like our wave is moving from left to right, it is x minus v times t. However, if it moves in the opposite direction, then it would be plus here, and means that this plus should be transferred on all other following equations in order to take into account the direction of motion from right to left.
Okay, thank you.
Mhm. Yeah, you're welcome. Thank you for your questions.
Thank
Okay.
you. Bye.
Thank you for your attention. Have a good day. Take care and see you on Wednesday.
See you. Bye.
Bye
Thank you,
bye.
Professor. Goodbye.
Mhm.